Hello everyone, my name is Yash Patel and this is my lab 2, which is on the motion of a falling object. So for the procedures and goals, so for this experiment, the motion of an object, so I used a crumpled piece of paper, was tracked falling down, and 3 different position versus time graphs were generated. The first one was from tracker, the second one was a computational model with only gravity, and the third one was a computational model with gravity and drag. And the goal of the experiment was to determine the effects of gravity and drag on the motion of an object and how it can accurately be predicted. And on the right, you can see some of the principles that were used for the model. So we used Newton's second law, weight force, and drag force, which we'll see when I discuss about the code that I used for the computational models. So these are data and measurements from tracker. So the mass of the crumpled paper I calculated to be 0.0145 kilograms. The initial position was 0.00289, 0 at frame 36, and the final position was 0, -1.743, and 0 at frame 57. And on the left, I can play the video of the crumpled paper falling down. So this is the code for the initial conditions, and this is only for gravity. So we included the ball's mass, which is 0.0145 kilograms. We also include the initial position and the initial velocity, and this is just the 0 vector because the ball initially starts at rest. And no drag is included, so the drag proportionality constant is 0. And this is the code for the simulation. So we set the while loop to run while time is less than 0.7 seconds because this was the time of the last observation. And drag force is not included, so the drag force is just the 0 vector, and weight force is included, and this is calculated by multiplying the mass times gravity times j hat, and this is all in the negative direction because gravity points down. And we also included the velocity update, position update formulas, and finally the arrow scale. And this is used to determine what arrow length in meters corresponds to 1 unit of force, and we calculated this by dividing 2 meters by the weight force. And this was important for the visualization aspect. So this is the predicted motion from the gravity-only model. As you can see, velocity is constantly decreasing since acceleration from gravity is constant, and the slope is not flattening over time, which is going to be important when we discuss about terminal velocity in the upcoming slides. And this is the code for the initial conditions with gravity and drag. The only thing that changes is that the proportionality constant is now included, and I calculated this to be 0.0083, and I did this by tweaking the value of the constant until the final position in tracker matched up with the final position in GlowScript. And this is the code for the simulation for gravity and drag, and the only thing that changed in this section is that the force of drag is now included, and I used the equation force of drag is equal to -b v squares times j hat. And this is the predicted motion from gravity and drag. Velocity is decreasing at a relatively constant rate in the beginning, as you can see on the left, but it flattens out at the end. And this helps us understand more about terminal velocity, which again we'll discuss in the upcoming slides. So you can see that the velocity tends to kind of flatten out at about 0.4 seconds. And this is the models versus experiment comparison. So the model position with drag lined up pretty well with the experiment position, except towards the end. And this is probably due to human error and the error in the tracking points on tracker. And the model position without drag had a steeper slope than the model position with drag and the experiment position. And this makes sense, right? Because drag is not accounted for, which means that the ball is predicted to fall at a faster rate because there's nothing counteracting the force of gravity. So terminal velocity with computational model. So if we take a closer look at the model with drag, we can see that the velocity begins to flatten out at roughly 0.4 seconds. However, in the model with only gravity, velocity is decreasing constantly. So this means that only the model with drag predicts terminal velocity, which is defined as the velocity at which drag force and gravity are both equal. And this means that the net force is 0 whenever terminal velocity is reached. So what if the object was thrown down? So even if the crumpled paper was initially thrown down, it would have no effect on the final terminal velocity. And we can see this on the graphs on the right. So the graph on the top shows a ball that is initially dropped at -3 meters per second, and you can see that the slope begins to flatten out at about 0.2 seconds, and then the graph on the bottom is a ball dropped from rest and it flattens out at 0.4 seconds. However, they're approaching about the same value, which is about -4.2 in both graphs. So in other words, as the models depict, even though the two objects may reach terminal velocity at different times, they're approaching the same value of terminal velocity. So yep, that's the end. I hope this was informative, and thank you so much.